In classical and quantum physics, superposition refers to a system existing in multiple states simultaneously until an observation causes it to collapse into one state. The typical approach relies on probabilistic wave functions, where observation is seen as the act that collapses these possibilities into a single outcome. However, today I'll present a different perspective. Superposition as a system of potentiality. In this view, matter and energy exist as waves of potential that crystallize not due to observation alone, but through interactions with higher-level organized systems. Let's explore this concept and critique standard interpretations of superposition by grounding it in hierarchical organization, where higher systems resolve the potentiality of lower systems. Superposition as potentiality, not probability. In the traditional quantum model, a system exists in multiple states at once, represented by a wave function, until observed, at which point it collapses into one state. This collapse is viewed probabilistically, but this probabilistic interpretation has significant limitations in explaining how systems stabilize and behave over time. In our proposed perspective, the wave function represents potentiality, not just probability. Each component of a system has a range of potential states, and it is the interaction with a higher-level system that dictates which state is realized. This removes the need for an observer to collapse the wave function. Instead, the system is part of a broader context, an overarching structure that influences and resolves the potentialities of its components. Think of a vibrating string on a musical instrument. Each point on the string holds a potential for various vibrations, modes, but the string as a whole, constrained by the instrument's body and tuning, determines which specific vibrations, states, will emerge. The higher organization, the instrument, stabilizes and structures the behavior of the string's individual points. Stability through waves and higher systems. Classical physics struggles with explaining how seemingly unstable or chaotic systems, like quantum particles in superposition, stabilize to form consistent reality. In contrast, we know that matter and energy fundamentally exist in waves that behave predictably over time. Waves represent the potential structure of matter and energy. These waves carry potentialities that provide the range for a system's behavior. A higher-level system, which could be a macroscopic object, an environment, or another quantum system, stabilizes these waveforms. The interaction with the broader system forces the lower-level waveforms to crystallize in a way that fits into the larger structure, providing stability. Picture a ripple in a pond. Each wave has potential directions and behaviors, but the shape of the pond, the wind and gravity determine how these ripples behave. The ripples stabilize because they exist within the structure provided by the larger environment, the pond and its conditions. Resolving indeterminacy through systemic interaction. In quantum mechanics, indeterminacy arises because a particle exists in multiple possible states until measured. The assumption is that an observer must collapse this superposition. This interpretation focuses too heavily on external observation. Indeterminacy is resolved by integration with a larger system, not just by measurement. A lower-level system doesn't resolve its state randomly. It crystallizes into a state determined by its place within a broader system. This shifts the responsibility for resolving superposition from an external observer to internal systemic interactions. The higher-level system overcomes the lower-level system's indeterminacies, forcing it to resolve in a way that serves the larger system's stability. Consider a crystal forming from a solution. The molecules in the solution have various potential orientations and positions, indeterminate states. But as the crystal structure forms, these molecules snap into a specific arrangement determined by the overall crystalline lattice. Here, the higher-order structure, the crystal, determines the position of the individual molecules. Interaction as entanglement and integration. In quantum mechanics, entanglement is a phenomenon where two particles become linked, such that the state of one instantly determines the state of the other, no matter the distance. This concept is often viewed as a mysterious non-local effect. Entanglement is better understood as an example of systemic integration. When two systems interact, they become part of a larger, connected system, and their behaviors are no longer independent. The wave-like potential of each particle is now shaped by the broader system, ensuring that any change in one component is reflected in the other, because both are now governed by the same higher-level organizational structure. Imagine two synchronized clocks. Once aligned, they remain in sync, even if moved far apart. If one is adjusted, the other will naturally reflect that adjustment because they are part of a larger system. The original synchronization process created an underlying coherence between them. The higher overcomes the lower. In traditional quantum mechanics, superpositions resolve through external forces, like observation, acting on a system. But this leaves many questions about what forces a system to resolve into a particular state. The key concept to recognize is that higher-order systems overcome lower-order indeterminacies. A system is nested within a hierarchy, and the behavior of the lower-level system is constrained and resolved by the needs of the larger system. This isn't a violation of indeterminacy, but an explanation of how potentialities at one level are crystallized into actual states by the structure and requirements of the larger system. The higher system dictates how the lower components should behave to fit into the overall structure. Think of a city's infrastructure. The behavior of individual cars on the road, lower system, is constrained by the road network, traffic laws, and city planning, higher system. The potential movements of each car are vast, but they ultimately resolve into predictable patterns due to the overarching organization imposed by the city's infrastructure. Superposition as structured potentiality. In this revised view, superposition is not about probabilistic collapse driven by observation, but about potential states that are resolved through interaction with a higher system. This approach moves away from the randomness and uncertainty often associated with quantum mechanics and toward a model of hierarchical organization where systems at multiple levels influence each other. Superpositions are resolved by the structure and dynamics of the larger systems in which they are embedded. In short, the higher organizes the lower. Superposition is not a state of randomness waiting for collapse, but a state of potentiality waiting for its role within a larger system. The implications of reinterpreting superposition as a system of potentiality, influenced and resolved by higher-level systems, have profound consequences for many areas of quantum theory. By moving away from the traditional observer-driven probabilistic collapse model, this framework opens up new ways of understanding quantum mechanics and its broader connection to physical reality. One of the most immediate impacts is on the quantum measurement problem. Traditionally, this problem asks why and how a quantum system collapses from a superposition of possible states into a single observed state. In the standard view, measurement by an external observer plays a crucial role in forcing the system into a definite outcome. However, under the potentiality framework, the act of measurement is merely one example of a more fundamental process, the interaction of a lower-level system with a higher-level system. Here, it's not the conscious observer who causes the collapse, but the fact that the quantum system becomes integrated into a larger, organized structure. This shift removes the need for an observer-centric interpretation and instead suggests that any interaction with a complex system can resolve the indeterminate potentialities of a quantum system. What we call measurement is simply one way in which lower-level quantum possibilities are actualized within a broader context, leading to a deterministic resolution based on the conditions of that higher system. This rethinking of superposition has significant implications for quantum entanglement as well. Traditionally, entanglement suggests that two particles, once connected, remain mysteriously correlated no matter how far apart they are, creating what Einstein famously called spooky action at a distance. In the potentiality framework, entanglement can be understood not as a violation of locality, but as an example of a structural linkage between particles that are part of a larger unified system. The entangled particles are not communicating across space instantaneously. Rather, their potential states are interconnected because they are governed by the same higher-order system. The broader structure in which they are embedded ensures that the resolution of one particle's potentiality is naturally tied to the resolution of the others, not due to any non-local action, but because both particles exist within a shared organizational framework. This interpretation shifts the mystery of entanglement from a paradox to a reflection of systemic coherence across different scales. The potentiality framework also offers new insights into quantum field theory. Traditionally, Particles are seen as excitations in underlying fields, and quantum field theory describes how these fields interact. In this new interpretation, the fields themselves can be viewed as fields of potentiality. Rather than merely representing probabilities of particle behavior, these fields describe the range of potential states that exist for particles, which are then resolved through interactions with other systems. When two fields interact, they impose constraints on one another, resolving the potentialities of particles into actualized states. This means that the emergence of particles from quantum fields can be seen as the crystallization of potential states shaped by the influences of larger systems. Instead of particles randomly appearing and disappearing from quantum fields, they emerge as part of an organized process driven by higher-level systemic interactions. The implications for quantum computing are equally profound. Quantum computing relies on the fact that qubits, quantum bits, can exist in superpositions of 0 and 1, allowing quantum computers to perform multiple calculations simultaneously. The traditional interpretation sees these qubits as probabilistic superpositions, waiting for measurement to collapse them into definite outcomes. However, in the potentiality framework, qubits are not merely in an indeterminate probabilistic state, they exist in a state of potentiality that is shaped by the higher-level structure of the quantum algorithm. The algorithm acts as the organizing principle that resolves the potentialities of the qubits in a coherent way. Rather than relying on the randomness of quantum collapse, the computation becomes a deterministic process, guided by the systemic constraints imposed by the overall structure of the algorithm. This opens the door to a new understanding of how quantum algorithms work, not as probabilistic exploration of possibilities, but as a process of orchestrating potentialities into a coherent, organized outcome. Moving to even broader scales, this framework offers a fresh perspective on the ongoing challenge of quantum gravity. One of the central problems in physics today is how to reconcile quantum mechanics, which governs the behavior of small particles, with general relativity, which describes the behavior of large-scale systems like planets and galaxies. In the potentiality model, we might understand quantum mechanics and gravity not as fundamentally different realms, but as different levels of organization. Quantum systems at the smallest scales exist in states of potentiality, while gravity, expressed through the curvature of space-time, acts as a higher-level system that organizes and stabilizes these lower-level quantum phenomena. In the potentiality framework, gravity doesn't need to be quantized because it functions as a higher-order organizing principle. Quantum systems at smaller scales exhibit potentiality, existing in waves of possible states. Gravity, on the other hand, represents the macroscopic stabilizing structure that influences and resolves these potentials. Rather than forcing gravity into the same framework as quantum particles, we could instead view it as the organizational force that shapes quantum systems from the top down. To give this more concrete meaning, we can think of gravity not as a force acting on quantum particles in a traditional sense, but as a shaper of space-time conditions that impose boundary conditions on the lower-level quantum systems. Quantum particles don't operate in isolation, but are embedded within the gravitational field, which dictates how their potentialities resolve. This hierarchical relationship could suggest that the problem of quantum gravity isn't about trying to unite the two domains under a single set of laws, but about understanding how gravitational systems organize quantum potentialities. This shift in perspective could reframe the search for a unified theory, not as a merging of quantum mechanics and general relativity, but as a recognition of how different levels of complexity interact to produce coherent physical behavior. For cosmology, this model offers a way to reconsider some of the most fundamental questions about the universe's structure. The anthropic principle, which suggests that the universe's constants are fine-tuned to allow for the existence of observers, might be unnecessary if we view the universe as a system of nested potentialities. The universe could be understood as self-organizing, where quantum-level potentialities are continuously shaped and resolved by the higher-level structures of stars, galaxies, and cosmic evolution. The constants and laws of the universe, rather than being the result of random chance or anthropic necessity, might be the natural outcome of systemic integration, where the higher-level dynamics of the cosmos influence and stabilize the behavior of the underlying quantum fields. This idea also extends to the Big Bang and cosmic evolution. Instead of viewing the early universe as a chaotic quantum state that somehow collapsed into the ordered cosmos we observe today, we could interpret the evolution of the universe as a process of systemic crystallization. The early quantum potentialities were resolved over time by the formation of higher-level structures, such as the emergence of galaxies and large-scale gravitational fields, that provided the organization necessary to stabilize the behavior of matter and energy. The universe, in this view, evolves not through random quantum fluctuations alone, but through a hierarchical unfolding of potentiality, where each layer of structure resolves the uncertainties and possibilities of the lower layers. Furthermore, this shift away from an observer-dependent universe might also resolve debates about the role of consciousness in quantum theory. If the potentialities of quantum systems are naturally resolved by their inclusion in higher-level structures, then consciousness is not required to collapse the wave function or to define reality. Instead, the universe itself is the observer, in the sense that its large-scale structure and dynamics impose the necessary conditions for lower-level quantum systems to behave in a determinate way. This view not only removes the need for anthropic explanations, but also aligns with a more self-sufficient, self-organizing cosmos. Finally, the potentiality framework suggests a profound reconception of time and causality in quantum mechanics. Traditional quantum theory treats time as a backdrop, but in a hierarchical system, time might be better understood as emerging from the resolution of potentialities at different levels of complexity. Quantum systems, nested within larger systems, are influenced by causal structures imposed from above, meaning that time itself could be shaped by the dynamics of the higher-order system. This could lead to new insights into how temporal phenomena, such as the arrow of time, entropy, and causality, emerge from the interaction between quantum potentiality and macroscopic systems. In summary, the implications of this potentiality framework reach across quantum mechanics, gravity, cosmology, and beyond. Instead of forcing all physical phenomena into the same quantum mold, we can view the universe as a hierarchy of organized systems, where the higher levels shape and resolve the potentialities of the lower levels. This new perspective suggests that superposition, entanglement, and indeterminacy are not random or purely observer-dependent, but are naturally resolved through systemic interaction. The search for a unified theory may not require quantizing gravity or invoking the mystery of consciousness, but rather understanding how systems at different scales of complexity interact to organize and stabilize reality. This shift in thinking could pave the way for a more coherent and integrated understanding of both the quantum and classical worlds, offering solutions to some of the deepest problems in modern physics.